Example 4, Part C. We want to graph the function f. So we're given the equation of the piecewise defined function above. We found the domain in Part A, negative infinity to 1. We found the intercepts, negative 5 halves, 0, and 0, 0 in Part B. So we already have intercepts we can sketch. So I will sketch my negative 5 halves. So negative 5 halves is negative 2.5, 0, and then 0, 0. Now we want to graph our left piece and then our right piece. So we know that the way that the equation is given, the 2x plus 5 is our left piece. It goes from negative infinity to negative 1. The right piece is an x cubed graph, and it goes from negative 1 to 1. So when we graph the pieces, we have to graph the left and right boundary of each piece if possible. So my left piece, I'll make a table, an xy table, and my y value in my left piece is 2x plus 5. So I'm making an xy table of values. Now my left boundary of this piece, it's unbounded. It's from negative infinity. So I can't obviously plot negative infinity, but I'm going to make a note in my table here that when I sketch that graph, I've got to show an arrow going all the way left, showing that it goes from negative infinity. Now, since there isn't a left piece, isn't there a left boundary of this left piece, all we have to do is show some point to the left of the right boundary. So the right boundary is negative 1. So just show some other point to the left. I'll show, just for example, a negative 3. So I've got to plot negative 3, or some point to the left of the right boundary, which is negative 1. So since there isn't a left boundary here, I pick any x value to the left of that right boundary, which is negative 1. So if I put in a negative 1 into this function for x, if I put in a negative 3 here into my function, 2 times negative 3 is negative 6, plus 5 is negative 1. Then if I substitute a negative 1 in here for x, 2 times negative 1 is negative 2, plus 5 is 3. Now, on my right endpoint, this endpoint, according to our equation, it's x strictly less than negative 1, parenthesis on that boundary of that endpoint. So that means that we actually don't have a point at negative 1, 3. We actually have a hole here, so I'm going to make a note. So when we sketch that on the graph, we're going to use an open circle. So let's go ahead and sketch that. So we have our points negative 3, negative 1. We have negative 1, 3. And that's where that point ends, the right endpoint. Oh, and whoops, and that should be the open circle at negative 1, 3. So this point, this piece we know goes infinitely to the left because its left endpoint, there wasn't one, it was from negative infinity. It goes all the way as far as to the right as negative 1, 3, and it's a hole there because there's no equal sign here on this inequality. So there's my left piece. We do want to label these points, all the ordered pairs that we label. So on tests and quizzes, I can give you guys partial credit, and if applicable, and I can read these clearly. So there's negative 1, negative 3. This was an intercept, negative 5 halves, 0. And here we go through the origin, 0, 0. And then up at this hole, it was negative 1, 3. So there's my left piece. Now I'll go to my right piece. And when I make my xy table now, we know that the right piece is defined by the function x cubed. So when I make my xy table, I'll have my x and then y equals x cubed. Now the definition of this piece says that it starts at negative 1 and it stops at positive 1. And it includes both of those. There's equals on both of those inequalities. So those will be filled in circles. So here I have a distinct left boundary and right boundary that I have to plot. So when you guys graph these piecewise defined functions, you have to graph the left and right boundaries, if any. Okay, so if I plug in a -1 here for x, -1 cubed is -1. If I plug in a +1 for x, +1 cubed is +1. So there are my left and right endpoints. So I want to start this right piece at the point -1, -1. Just label that right there. And I want to end it at +1, +1. Now we know the shape of this cubic function is that increasing squiggly snake shape. So when we connect these, we want to make sure we don't make a mistake of making it linear and sketching a straight line through. So we want that kind of little curved shape, that little curved snake shape. So we can now see the two distinct pieces. Here's our left piece. Our left piece is linear, a 2x plus 5 graph from -infinity to -1. Then at -1, this graph jumps down to a cubic function, the squiggly shape, from -1 up to +1. Part D, is f continuous on its domain? So if we take our pencil all the way left as far as this graph goes and start tracing left to right, I'm continuing along. Now I hit an open circle and there's a split in the graph and I jump down to this piece. So since I had to lift my pencil to jump to that second piece, we know this graph is not continuous on its domain. Part E, based on the graph, find the range. So we know the range is the set of all the y values for which this function is defined. So if I take my pencil all the way down to the lowest y value, which goes down to -infinity, I trace continuously all the way up here until I hit this open circle at a y value of 3. And then the graph never goes up any higher in the other piece. So I know this graph is defined for all the y's from -infinity up to 3, but not including 3 because of that open circle. So in interval notation, parenthesis, -infinity, comma, 3.